Okay, students, welcome back, and let's get going for today's class. I'm going to give you some exam two comments, and then we will go and talk about circuits and magnetic forces between wires and so forth, and eventually induction. And our target is basically induction, because electromagnetic induction is where we first figured out that electricity and magnetism are one common force. But before I do that, I have a few little announcements to make. First of all, no office hours today, but I'd probably be out in the hall after class for a few minutes. So if you want to chat with me then, but otherwise I'm going to try to blaze on home. My back is feeling a little bit better, but it's still not out of the woods. So I have to use a stupid walker for a few more days, I think. Anyways, hopefully I'll be back to disco readiness in a few days, maybe next week by this time. And I know you guys are all into disco and stuff. So, all right, exam two comments. Uh, just talk about a few things, and what I'm going to show you about exam two. I want you to think of it, take a note of what I'm talking about, so that you can improve on exam three. So let's just go ahead and you follow along with me and see if we can improve your performance again on exam three. So a few of the most important items on the test. Now these are specific items. And here's one of them, the brain burner about the discharging capacitor. You know, how long does it take to get to 25%? So you not only have to look at which curve is discharging, you have to know that. You also have to know what the meaning of a half-life is. Now, up here, I want to bring your attention to something. And now you guys don't see this, unfortunately. This is in the teacher's version of the stats. And I really can't release any of this stuff to you guys, unless I make a total PDF of it, but I'm not going to do that. And that's the discrimination index up here at the top. Now this one is positive 0.36. And what that does is it tells you, it looks at the answers, like here are the answers for that test. And it combines it with the percentage that get it correct. And it tells me that the students that have a high score on the test did this one correctly, and that the students with a lower score didn't do this one correctly. All right. And this one, and you can analyze these percentages over here. So 84% got this one correct, but 3% got this answer and it's incorrect. Nobody chose this one. A few of you chose this one, 8 students, and then another 4 down here. Now the chances are that these students that didn't answer correctly also got a low grade on the exam. And you can analyze this in terms of information theory and figure out how many bits of information is in this. This is relatively one binary digit of information stored in this set of responses here. And so that tells me that it was basically one task that you failed to do. The people that didn't get this one right, there was only one thing that they had to do, numerically speaking. And basically that's, in this one, the answer was in chapter 31. If you read chapter 31, as I mentioned in my annotations, in chapter 21.6, you could have gotten this. Now, most of you did get that. So to me, what that tells me is that if you want to improve your score, if you had a stinky score, pay attention to the annotations and do what they recommend. That's what this one was. It wasn't make or break, but it was a good discriminator. Now here's my comment on this. It's a spread, and when I show you clicker questions afterwards, and I say we got some splaining to do, that's when there's a spread of answers like this. Now this one's got a strong correct component, 84%, but it still has a lot of information in it. So this tells me a little bit about the complexity of your thought processes and stuff. So let's take a look at another problem. And this one, now look at the discrimination index up here. Zip zap, all right? And why is that? Well, 100% of the students answer this correctly. So theoretically, this conveys zero information. Everybody got it. So I don't have to ask questions like this on the test in order to see, the state of things in your minds. Okay, this one, it's a lock. Everybody's got it. We're good. All right, and zero discrimination. So this lack of spread in the answers conveys exactly zip zap. So in terms of information theory, this is zero entropy. Anytime, you know what else this is like? This is like if you're playing dice with somebody and they have a pair of dice that always comes up 7, right? Every time. What that tells you is you don't want to play dice with that guy or bet against that guy, bet against a 7. You don't even have to pay attention. The dice convey no information. Once you see it, all the other rolls of the dice. Okay, so that's the same thing here. It's 100%. We don't have to ask this question. We can hang up the phone, so to speak. All right, next question I want to review with you. This one surprised me, but discrimination index of 0.31, and this up here shows me that there's still some misconceptions. A good 75% got it correct, but this should have been 100% or darn close. And you can see that there's 95 respondents, but about a quarter of the class got it wrong. And if you're one of the people that answered protons and electrons both move in the same direction, that to me you got caught napping on that. Nobody should have gotten that one. The other one, yeah, I can maybe see somebody making an honest mistake about that, but all right. Now this one is question 2699, and I'll explain what that means in a minute. That's on our blurb sheet. The information content of this one is entropy is 0.797, so that means one decision, and that's what that is. So this is the second one. This is the I squared R question, and this one, notice we have a little bit more spread between the other three. Now, I have no idea how anybody would think constructive or destructive interference. This was supposed to be a giveaway. This is supposed to be some free dineros, and for 85% of you, it was. See, I can write questions. I can put a test together. If I put in a bunch of brain burners, I have to throw in some questions that are fairly basic just to get them done. But this one, considering this one is basic, that's waves. And we're not talking about electrons as waves in this part of the class yet. So it's bad. All right. Now, some of you got tempted by momentum transfer from electric field to electrons. And that's what and that's actually tempting because the electric field does put some momentum into the electrons. You know, they have a drift velocity and so forth. But that's not what I squared R is. And this one, you want to, this one's basically one mistake, one thing that somebody didn't do. And in my opinion, it would be somebody that didn't read the annotations in chapter 20.4, because that's where I talk at length about it. And I highlighted it in chapter 20.4 as well. So, um, now this one is a problem, you know, discrimination index 0.41. Anything above 0.25 is considered good. And there's other ways to analyze data, results and stuff, but that's how this one goes. Now, I normally don't do this on Scantron exams, although I could, but Web Courses does it for us automatically, so that's why I'm showing it to you. All right, the next one I want to go with you is a little bit of tough sledding, kind of like these guys trying to pull a sled across a parking lot with no snow in it. I don't know. Anyway, so this was the one. Now, this one has a low discrimination index. It's 0.21, still positive. And you can get a negative discrimination index if the students that do well on the test answer incorrectly and the students that do poorly on the test answer correctly. That's like a negative correlation. But this one it's positive, but it's not very strong. And this one, the difficulty factor, the number that answered it correctly, is 41%. Right? And for this one, the entropy value, which, you know, maybe I'll make a little mini lecture about entropy because that's germane to our topics this semester. Anyways, the entropy value for this one is 1.82. So that means two decisions, 2 bits, 2 binary digits explain this answer. Two things that students didn't do. All right. Now, I don't know what 2 decisions or 2 things you didn't do, but by golly, you know, we definitely talked about this concept. When delta Q over delta T is proportional to Q, you're always going to get some kind of um, exponential time dependence. Now, this one, I'm unhappy to see it at this level of performance, but that's the way it is. Now, this one's question 2525. And I told you I would explain that, so let me explain what those code numbers are in case you haven't already figured it out. This one, and now I'm going to talk about the error list and the blurb sheets that you may have noticed in web courses. Now, we don't get individual printouts like we do with Scantrons, all right? So the way that I make up for that is I make an error list, all right? So what I do is I analyze every student's answers for every question, and then I make up a short list. A few of you aced the test, actually, which was nice. But for those of you that got some wrong, you have a little list, and it's basically, those are all the internal code numbers for the question. So that's what I go by. They're unique identifiers for each question. And you find it on your grades page. Now, here's what it looks like in your grades page. All right. So here's your grades page, for instance. All right. And if you go down to midterm exam 2, right down here, you'll see a little icon for text messages. Okay. If you click that, then you'll get the error list. Okay. So here's the error list. So John Q. student had 2522, 2561, 2562, and 2719 incorrect. All right. Now everybody that took the test has got that, except a few of you aced it, and you just have the word ace in your comments. So you don't have an error list, but everybody else has got a bunch. All right. Now, why is that important? Well, You then go and look up the blurb sheet. Now here's the blurb sheet, and it's a PDF, and it basically is a list of all those ID numbers, 25, 22, and so on. And then next to it is a little blurb about each item. So kind of looks like this. So 25, 22, brain burner, the evolution of the capacitor state, two curves, time to 25% of its initial load. That's enough to tell you the gist of the problem, but not verbatim. So I don't publish verbatim. Used to be in the old version of web courses before we shifted over to Canvas, I could embed this information a little. Is there a question? Good. All right. It used to be that I could embed a little blurb about each question on the quiz and then or test, and then after the test, you could see your score for each question and the blurb, not the question. But I can't do that now in Canvas because Canvas only lets me uh, publish the question itself. The blurbs afterwards, it doesn't have blurbs. It has garbage, in my opinion. And because it's Canvas's way or the highway. But I defeat Canvas in this manner, and it takes me a little bit. I'm getting good at it. It only took me a couple hours with you guys. But I got to analyze a big spreadsheet of all your answers, and then I got to put together your error codes, and I got to use. Raise your hand if you've ever used the computer command concatenate or cat. Ever hear that? No, nobody in here. It's a concatenate is a Microsoft Excel and Apple numbers command. In computer language, it's usually cat, um, and it's concatenated. It just means string together. I string together a bunch of whatever code number you have for your incorrect answers, and nothing for the questions that you got right. So you know, so that's how that works. So here's 25, 25, the one that we flailed on. And by the way, students, that was the only question that the entire class flailed on. 25, 25. Exponential time dependence. But there it is. And all the other ones, are down there. So that is linked in the blurbs page in web courses. Raise your hand if you've taken a look at the blurbs page. All right, a few of you. Go ahead and do that. Get your error list, just write it down in your notebook or something, and then go to the blurbs page. And the reason that Melanie Del Toro, the reason I put this together for everybody is so that you can use it as a little mini study guide for the final, right? So you'll know, okay, if you got 25, 25 on your error list, when the final comes, better bone up on, what chapter did you say that was? Okay, and you go back and look at the either YouTube or the textbook and do a little extra studying on that. And hopefully, if I ask a question like that on the final, hint, hint, uh, you'll get it right this time if you use this as a study tool. All right, so the blurb sheet and the error list together are kind of a nice study tool. So now, last thing I want to point out to you is down here at 2740. And let's just focus in on number 2740. Magnetic monopoles discovered September 31st, 2018. Now, what's the problem with that? There is no September 31st in 2018. Didn't you know that? Not only 2018, but in any other year. So if you see, and this was a true false question. Now, most of you got it right, so I'm not, but a few of you.
It looks like a typo.
Now, if Attention, Achtung. If you see me write an option in multiple choice or true, especially true false, if it's got anything about September 31st, that's my standard trick. That's kind of a, see, oh, wait a minute, that can't possibly, nothing in that true false can possibly be true if September 31st in any year is in there. All right. So that's just like me using a Chuck Norris option in a clicker question. It's probably not the right answer. So, but I'm just, sometimes I run out of things to type in for multiple choice. So I put in a Chuck Norris option. But in this one, sometimes I run out of things to say that are wrong with, things. And so I put in a September 31st. And by the way, this is a famous novelist's trick. There's a famous novel about World War II, the Battle of Britain. And it was a typical day for the Battle of Britain on September 31st, 1940. And then at the end of the book, they say, of course, there was no September 31st in 1940 or in any other year. So that's why I love this one. Anyways, all right, now the bonus problem, I'm still working on it. And some of the answers look good. Now, up here, there's a lot of pain. I shouldn't have assigned this problem. Look at these equations. Look at this one. I2 is equal to negative 13 over 23 times I3 minus 12 over 23. That's one of the loop formulas after the junction formula has been plugged in. And so that is a menace to navigation. Now here's, I worked this out a couple times to check my work. And here's the second one over here. This is the one with I3 and I1. And it's in here. And so you can see that you've got a lot better numbers up here, coefficients to I3 and I1. So unfortunately, I have to look at everybody's equations if you got it wrong. And I hate to say this, but there's a fair number that didn't get it right. Okay. And you'll find that out in probably next week. I'll be all done with that stuff, and I'll be able to hand those back. So these equations are kind of one of these situations where, why did I do this? But we're gonna get them graded, and you're gonna get them back, and I think a bunch of you will get at least some partial credit, anyways. So that's nice. So for those of you that aced it and get even a point in the bonus point problem, you're going to be off the charts. You're going to be over 100%, which is nice. All right. And some of you will claw back a few points from the, that you missed on the multiple, which is good. All right. Now, for those of you that did good on both, exam 1 and exam 2, just figure this as boost whatever bonus points you get here as boosting your exam 1 grade. If you did good on exam 2, then this one will boost your exam 2, your exam 1 score. But my opinion is that exam 1 is going to be dropped for many students. But in any case, the bonus points, whatever you get, they will not go away, even if I end up dropping exam 2, which is possible for some of you. All right, we're going to do magnetic force on a wire on the document cam. So let's switch over to document cam and just work out a couple things. And what we're going to be doing is, Kendra, can you operate the panel over here? What we're going to be doing, boy, this stool is murder on my back. All right, let's see if I can do a little bit better here in this chair. What we're going to do just sit on the chair there, and I'm going to ask you to go to the next slide here in a few minutes. Don't do it yet.
It's just space bar, right?
Yeah, space bar will bring you over. All right. First thing that we're going to do is the magnetic field of a wire. So let me get my writing implements. I'll use this one today. And we're going to do a clicker question after this. So I want you to be very, very alert. Okay. All right, so here we go. This is October 23rd. Star date, I don't know. PHY 2054. All right. Let's go ahead and draw a picture of a current carrying wire where the current is coming out of the paper. All right. And concentric to that, draw yourself a dotted line circle of any size that you care for. And that's what I'm going to do over here. And that's a pretty good circle. All right, I'll trace it in a little bit with my pencil here. All right. Okay, it's a little bit more visible. Okay, now let's make the radius of this R. All right. Now, we know that if the current is coming out of the page, that the magnetic field vectors at this distance are counterclockwise. So I'm going to put a dot up here at 12 o'clock, all right, on my circle. Now up there, counterclockwise means to the left. So I'll call that B, magnetic field B, subscript W for B of the wire. My pencil's breaking. Let me get my other pencil here. All right, so, and go ahead here to 9 o'clock, put a dot down here, and make your arrow tangential to the circle, and try to make it the same size. All right, and I'm going to go over here to about 4:30, and you can do one over here. Same size arrow. And you can draw B of the wire wherever you would like to write it. But so the direction we have, and we know that it gets stronger the closer to the wire that you get. All right. But what actually is the magnitude of this wire? We've got the directions. The right-hand rule tells us that. But what is the magnitude? So let's write this down. The magnitude of the magnetic field of a wire is equal to this fraction. Now there's a new constant here, mu naught. That's Greek lowercase mu times the current in the wire divided by good old 2 pi r. All right. Now there's a ton of calculus in that. All right. So we're going to bypass the calculus and go straight to the formula. All right. Now, what is the value of mu naught? Mu naught is in the metric system 4 pi times 10 to the minus 7 Tesla meter per ampere. Okay, so that's a, um, do you remember what this is called? The it's either permittivity or emissivity of free space. It's a constant of nature, and it's related to the speed of light. Uh, and and this is the value in the metric system. So this is in terms of Teslas. Now we could use Gauss if we wanted to, and then this 10 to the minus 7 would be a little bit smaller, but it's still, you know, Teslas is what we're going to work with. All right. Now,
Permeability of free space.
permeability of free space. And this is a term that traces back to the 1800s, the days of Michael Faraday. All right, so that's what this thing is. And it's just a constant. And, you know, here's one way to look at it. You know, you have the source of the field in the numerator, just like the source of the Coulomb field, the charge is in the numerator, KQ over R. You have an R in the denominator, same as for the Coulomb field, all right? So remember, the Coulomb field of magnitude is just KQ over R. So mu naught is a little bit like that, except that we encode it with a 2 pi in the denominator for reasons, and you might think to yourself, how come I have to have a 2 pi down here in the denominator of the force law or the field magnitude when I already have a 4 pi up on top? I cannot answer that, but some guy in England or Germany or something with a big mustache, you know, back in the 1800s decided to use this encoding of these constants. All right, let's say typical classroom, the current is 2.5 amps. And let's go out to a distance of 0.35 meters. Okay, so 35 centimeters. So that's about 7 inches or so. No, let me take that back. 7 times 2 is, it's about 14 inches. So that's about, you know, that's out here, you know, from the wire. So that's pretty far away, but let's calculate it. All right, now I'm going to change my, all right, so I've got mu naught which is 4 pi times 10 to the minus 7 Tesla meters per ampere oh, times 2.5 amps. And then down in the denominator, I've got a 2 pi and a 0.35 meters. Now you can see here that the meters cancel. I'll use my red ink for that. And that the amperes in the numerator go with the per ampere in the constant. So those cancel out. So I'm left with Tesla. That's good. It's a magnetic field. And so basically 4 pi over 2 pi is 2 times 10 to the minus 7 Tesla. Write that, minus 7 Tesla times 2.5 divided by 0.35. Right, and the units are Teslas. So so what do you get? You have, so this is basically 5 times 10. So this is 5 times 10 to the minus 7 Tesla over 0.35. So that's 5 times 3. So it's a 1 point, what is this, 1.57 or something? Let me do this. All right, 5-second EE minus 7 divided by 0.35. Okay, 1.42857 blah de blah times 10 to the minus 6 Tesla. And that is about 1.42, 1.43. I'm going to compare this to Gauss. 1.43 times 10 to the minus 2 Gauss. Because the Gauss is 10 to the minus 4 Teslas. All right. Now, the reason that I'm doing that is because I want to compare this to the Earth's magnetic field. All right. So that's what we're going to do on the next page. All right. Now, I looked up on the internets the magnetic field of Earth in Florida at our latitude and longitude. In Orlando. And the magnetic field, here's the surface of the Earth. And so the magnetic field is not going to go straight into the Earth. But what we're going to do is we're going to calculate the horizontal component of the field. So that's this part. Okay. And what that does is this horizontal component, I'm going to use the symbol, the parallel symbol to symbolize that because it's parallel to the surface of the Earth. Because when you hold a compass, you hold it so that the compass needle is parallel to the Earth, and then you look in which direction it goes, right? So it's interacting with the parallel component of the magnetic field wherever you happen to be, all right? Now, in Orlando, let's see, I wrote this down here. I looked it up this morning. Magnetic field of the Earth, parallel to the surface in Orlando, is 246.04.6 times 10 to the minus 9 Tesla. All right, now that's the, I think it's a NOAA website or US Geological Survey website that provides that. Now let me convert that to 246.046 times 10 to the minus 7 Tesla. All right, so that's the field strength at the Earth. Now, what we're going to do is make a ratio. The magnetic field from the wire divided by the magnetic field from the Earth parallel to the surface of the Earth. All right, so here's my ratio, 14.3 times 10 to the minus 7 Tesla, numerator 246.046 times 10 to the minus 7 Tesla. Okay, 10 to the minus 7 Teslas cancel. So you're looking at 14.3 divided by 246.046. And that is about 0.0581. Can you verify that for me? And, you know, I'm going to do the same.
I got that.
0.0581. Anybody verify me at 0.0581? Raise your hand if you verify. All right. Okay, so what that tells you is The magnetic field of the wire is not even 6% of the magnetic field of the Earth. So the wire is not going to deflect the compass needle a whole lot. Let's figure out how much it does. If the Let me think. If we arrange the wire so that the magnetic field of the wire, which, we could do it just by rearranging the wire, it's perpendicular to the magnetic field of the Earth, like this. So if I have that, that's going to give me maximum deflection. If I turn the wire 90 degrees away from that, it's going to give me zip-zap deflection. So I'm not going to tilt the needle very much unless I'm perpendicular. So I rearrange my wire. Basically, what I do is I rearrange my wire so that the wire is parallel to Earth's magnetic field. So I get my wire going north-south, all right? And then my magnetic field of the wire is going to be perpendicular. Now my tilt angle is going to be, all right, let me go ahead and make a rectangle here. You're going to be calculating this tilt angle here in a second. All right, so here's the resultant magnetic field here, all right, at angle theta, all right. So the arctangent of that tilt angle, that deflection angle theta, excuse me, the arctangent of 14.3 over 246.046, that's equal to the deflection angle theta. And who gets an angle for that? Give me the nearest degree of deflect. And you're going to be doing another. Yeah, can you go to the second page now? Good. All right, who's got a deflection angle? Raise your hand. Bradley. Who else has got a? Okay. Mackenzie. Right. What do you got, Mackenzie? 3 point something? Anybody for 3 point something? Arctan. Okay, good. Rachel Dupuy's got it. Anybody else over here on this side's got it? 3 point. Make sure you get it. Carly Gonchak, did you get it? All right. Make sure you get it because you're going to be doing this, Cassidy, on the first clicker question. All right. You're going to be doing a different deflection angle. All right. So I want to make sure you get that squared away. So my wire has a weak deflection from the wire's B field. All right, now let's go ahead and switch to laptop. I'll operate from here. You can keep sitting there. All right. Now, what we're going to do now, get your clicker out. We're going to do a multiple choice question. All right, let me stop this for just a second. So here's your first multiple choice question for the day. How can we make the deflection angle theta bigger? In other words, larger than 3 degrees. All right. So go ahead and make a vote, make a decision. Good. Yeah. Because there's only 3 degrees. Yeah, so we didn't, so in other words, Mackenzie, we didn't get like 70 degrees or, if it was at that angle, and if it was really strong, it would totally go 90, you know. So that's interesting. Let's see, these are both correct. All right, 10 seconds to vote. 10, 9, 8, 7, 6. What? Hit the refresh key. All you have to do is type in a letter. A, B, C, D, or E. 6, 5, 4, 3, 2, 1, 0. All right, now, here's our formula. For the field strength, R meters away from a current carrying wire with I amps. All right. Now, if you want to make that quotient bigger, there's 2 ways to do it. All right. You can increase the numerator, and 69% of you voted for that. All right. So that's good. But a smaller group of you, 27%, chose decrease R, make the denominator smaller. And that is righteous too. So there's a couple different ways to handle this. Now, what we're going to do for the next question, this is going to be a brain burner. I'm going to give you several minutes to work it out. All right. We're going to keep the amps 2.5. So we're going to ditch option A or option B. Oh, by the way, option F cannot be selected on this problem. What do you see wrong with option F? All of the above includes none of the above, and none of the above includes all those things. So, so what is F actually? It's like, yeah, and there's no F, and there's a reason that I put it as F, just to. But believe it or not, I actually wrote a test one time that had all of the above below, none of the above, and students were really giving me the business about it. Anyway, all right, so brain burner time. Hit your refresh key one more time. We're going to do a numeric question. Let me just pause this for a second. So here's your next question. At what distance will the deflection angle be 20 degrees? Oops, that's supposed to be a question mark at the end instead of a slash. All right, now type in your numeric part of your answer to the nearest 0.01 meters. All right. And I'm going to do the same. Let's see if the students.
Keeping the same values, right?
Yeah, keeping the amps the same. So we decided to keep the amps at 2.5.
So you work backwards and find the wire, and then go backwards again.
How many answers have we got? 10?
Yes.
Why don't you circulate around? See how they're. Brad, Brad, can you move that red chair out of the way? Yeah, I'm gonna come through behind you. Oh, Maya, can I get through there, please? Hmm. Good triangle. Okay, I'm trying to scamper through here. Jordan, you're working on your calculation there? Theta equals. Hmm. So basically what's going to happen is this numerator has to change, right? So how much do you have to change that numerator? Oh my goodness. Look at those notes. They're nice, but are they righteous?
But she did have a question though. Like you're wondering. Like current wasn't like given. Like
Hmm?
is it the
No, current is still 2.5. Yeah.
okay.
Remember I had that on the previous slide.
Yeah, I
Ooh,
just didn't know.
nice notes, but I caught you napping on that one. Yeah, 2.5. So use a 2.5 again. But what we're going to change is this junk down here.
Okay.
So it's gonna have to be smaller.
Okay.
So I mean, so you shouldn't get like 0.39 meters. You're gonna get something smaller than 0.35,
Alright, thank you.
right? But the question, yeah. So change everything. Can is whose bag is this back here?
Sorry.
I don't want to. I don't want to run it over with my walker. Yeah, it's a real speed bump. I'll take my tour of the back 40. What's going on back here? Oh,
That's my
mm-hmm. Yeah. Now you got to figure out what your R is going to be. So that's the. But you also know the magnetic field of the Earth. That's 246, all that business. 246.046 times 10 minus 7. Daniel, could you move that chair out of the way? No, it's still in the way. Move yourself back to where you were.
it's a
Yes, but that's where I'm going.
here.
No, I'm going over in that direction. I want to make the corner over. No, I don't want it there. Move it this way.
It was just so you could get by.
Yeah, no. Okay. Shove them all in there.
Yeah,
Except Daniel, you should have stayed right here. That's all you need to do.
yeah.
Just shove those things out of the way. All right, let me scamper through here. My cat-like quickness. All right. Making a calculation over here. You got it? What do you got?
So basically, we're going to apply it 30 degrees, 20 degrees. We put it back in the other equation, arctangent.
Carly, you've done it again. See, she's blushing. Carly's blushing. It's hard to be humble, I guess. Oh, really? A deep. It, all right. All right. What's going on over here? You guys making some progress?
don't know if it's right.
Let me see what you got. Here, I'll come over. No, too small. Let me see what you got. Let me get my specs. Now, what's this? How come you're canceling? You're not canceling R, are you?
No.
All right. Now, what's 89.51?
That's what I got here. I set. I took the marketing.
Oh, yeah. Okay. Okay. Good. Yeah. This is good. That'll.
I took the tangent on both sides.
Yeah. So what you're gonna get? That's, so this is the same as saying tangent of theta or tangent of 20 equals this junk. Right? And so you went, and that's times 10 to the minus 7 Tesla down
I
here.
forgot that part.
Oh, really?
Yeah.
Yeah. So is that really true? Is that the tangent of
That
20?
would be the same.
No. So tangent of 20 is.
Oh yeah, yeah,
Yeah.
definitely.
Yeah. All right. So now I see where this is coming from.
Yeah.
Yeah. Now here's where you. This constant is 4 pi times 10 to the minus 7 Tesla meters per ampere. Okay. And so this per ampere here cancels out the amps here. All right. And then meters and meters, but you got to solve for R. So this is, let me see your rig.
I just did 10 of 20 on my calculator.
Let's just verify what you got here. All right. Okay, so tangent 20. Okay. What you got here? Times 246.046 equals. All right. Now let's multiply by 1 EE minus 7. All right, so there's your, and that's really what you should be working with. Okay. And that's going to be Teslas. All right, so 8.955 times 10 to the minus 6 Teslas. All right. Then you just got to put these things back in here and solve for R. So, and CJ, it's going to be a number. It's going to be a whole number between 0 and 35. So in other words, or between 0.00 and 0.35. So you're not going to have to go like 10 to the minus 7 meters or anything like that. So if you come up with 10 to the minus 7 meters or something, that's too small. It's going to be bigger than a centimeter. So it's between 0.01 and 0.25. All right. Are you working by yourself?
I was.
What about the other guys that are usually here?
Oh,
Don't they-
Kevin was here.
Yeah, Mauerman, you're over here usually. That's your team?
that's how you get point.
Yeah. That's Montez, Chris.
Okay, so now, so this is the first part. So let's work these backwards. Okay, I know. So that, and then, so they put on top, originally we got 42.3 divided by this. So now we got,
Alexandra, you guys making progress over there? You did?
I think so.
Let me see if I can verify. He has neat handwriting? Yeah, but how come I see a big scratch out there? What's that? Oh, you had a little accident? It's all right. Did you click it in? Huh. Are you sure it's the right answer? That settles it. When she goes like that, she means business. That's it. No more fooling around. All right. Gianna and Emily and everybody.
I did a really long, you got it, but I ended up with that. Yeah. I don't know if that's like too long of a way though.
No, look,
It's fine.
there's more than one way to skin a cat. I'll show you my method in a few minutes. Madeline, can I scamper through there? Madeline, can I move through here? Thank you. Well, fellas, what's the verdict over here?
Back again. The boys are back.
Dude, I thought I could burn up some people's brains here. Ooh, okay, nice. Very nice. You guys got your answers?
Yes.
Okay. But are they correct?
Yes.
Okay, 1 minute to get your answer in. Pretty good, it looks like. All right, now what I'm gonna. Yeah, I got it. Yeah. No, unfortunately, if you understand relativity in geometric terms, then you can never say that trig is not physics.
I mean, it's not the concept of physics in this problem, basically. I mean, it is physics. Trig is made
Trig
by
is physics,
Yeah.
right? Trig is space-time, and trig is part of that. It's just the way that the universe is. I mean, what if a squared plus b squared was equal to c to the third? But it's not. What if pi r squared was pi r to the third over 7? That's no good. There's a physical reason that distance is the sum of two squares spatially, but space-time distance is spatial squared minus temporal squared. That minus sign is everything. And it's related to the idea of rotation. They're both related to the idea of rotation. You haven't had my relativity class, so you're not familiar with these advanced concepts, but It's all geometry. I tell you, black holes, it's all geometry.
Yeah, maybe I lunch with the dean candidate Creel, and he was the dean of the college we went to. I forgot what it was called. UFPL, something like that. And he was talking about how one of his students was using black holes as lenses to make like a makeshift microscope in space, or a makeshift telescope. But you know it's hard because of all the aberrations in black holes. You can technically use them as lenses. It's just not, you can't prove that it's correct, you know, because they have to put material in
Yeah, because we can't put a black hole in the lab, not yet. We can't even put a hole. But you know, some of the interesting thing is there's some sonic acoustics sonar type stuff, physics, where they have this. Have you heard this sonoluminescence? Apparently, you can simulate some black hole physics with sonar. And yeah, that's kind of it. I never have dug into it, but all right, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And I went around. Oh my goodness. Look, wait a minute, I'm going to make this big, ginormous. So, because you guys are, uh, well, what can I say? You guys are geniuses because this is the correct answer. And I see a bunch of you with that. Now, here's somebody 0.056. That's a factor of 10. Here's another factor. Whoa. That's a factor of 10 to the minus 9 or something there. But let's go over the solution to it and just double check. I've got mine already written out. Kendra, can you go to the document cam, please? All right. So here's where we finished off. This angle was well, it's a small deflection angle, about 3 degrees, right? Um, so the question is, how do you make this numerator bigger in order to get a bigger angle? Now, we chose 20 degrees, and we could have chosen 45 or anything else. So here's what I did. I took the tangent of both sides of this, and basically that's what I've got here. Tangent of 20, that's my new deflection. That's what I want. And that's equal to the ratio of the wire's field to Earth's magnetic field. All right. Now, this was too small at 0.35 meters. So the key is to take this thing apart, the magnetic field of the wire, and then get R from that. So, and I saw a lot of you guys with this. All right. That's good. Now the next step is to slap that ratio apart. So the magnetic field of the wire is whatever Earth has times the tangent of 20. Now tangent of 20 is just a numeric factor. So but I'm going to leave it as tangent of 20 for a second. Now I'm going to put in the magnetic. Now over here on the left, here's the magnetic field of the wire. And notice that I have some erasing here in the middle, because I had 2 times 10 to the minus 7, because remember up here, no, it was over here on this one, the 4 pi times 10 to the minus 7 over 2 pi. I just simplified that to 2 times 10 to the minus 7 up here. All right. Now that was on the previous deal. Now I've got that same factor here. So here's my 2 times 10 to the minus 7 and my amps. But this, on the previous problem, when I was over here, I canceled out meters and meters. And so this was just Teslas up here. But with this problem that we're on now, I can't cancel out the meters because I don't know what that denominator is. I don't know what R is. So I have to leave this as Tesla meters. All right. Now the amps cancel. So this is 2.5. And I have a factor R. So now all I got to do is get R by itself. All right. So I cross multiply R to the numerator on the right. The magnetic, all this junk over here, tangent 20. And this is 246.046 times 10 minus Tesla over here for the magnetic field of the Earth. So here's my formula for the distance R. And notice here, okay, this stuff up here, this numerator is basically 5 times 10 to the minus 7 Tesla meters. The numerator is R. And then I got the Earth's stuff over here. Now, here it is again. Here's that numerator, 5 times 10 to the minus 7 Tesla meters. And then here's some Teslas in the denominator from Earth's magnetic field. And then here's my tangent of 20. So my Tesla cancel right here and here. And I just have meters for my only unit of measurement. And that's good because I'm trying to calculate a distance. Now I just do some plug in. And I find that I get 5.58 times 10 to the minus 2 meters. And to the nearest point, 0.01 meters, that's 0.06. And I saw a lot of people with this, and I hope you typed in 0.06. And if you did, you're looking righteous. So that's the brain burner. All right. Now this is going to be embedded in the YouTube after class. So don't feel like. But that's how I did it. Now I looked at some people and they had just ginormous pages of calculations, but still got the right answer. All right. So this is the way I did. CJ. Well, right here, this is scientific notation for my calculator. All right. And that's the same as 0.058 meters. All right. Which at the precision I asked for rounds up to 0.06. But it's really, the same as, that should be 0.058. 558. Okay. And so that rounds up to 0.06 or approximately 5.6 centimeters. So that's, that's about 2 inches long. So maybe the length of your thumb, which is a lot closer. 7 times closer. All right. Another question. Can you see if there's any questions over there? No, from the students. All right. Next slide, please. Now what we're going to do is the magnetic field inside of a solenoid. Switch to the laptop, please. And a solenoid, it's not like some kind of weird alien, from space, from the planet Solon. It's I don't know, it's a Latin term, I guess, for making a tube out of a wire. Go ahead to the next slide, please. Here's a diagram from your textbook. And a solenoid, you can see it up there connected to that car battery. All right. And your car has what we call a starter solenoid in it. And it revs the engine or turns the engine over as the spark plugs start to fire. And it's basically a big coil. All right. And if the current in the front of it, see those blue arrows? Let me get my cursor over there. I'll switch over here. These blue arrows across the gray coil, the coil is known as a solenoid. Okay, they're going up. So they're going up like this. So your fingers of your hand curve in the direction of the current, and inside the loop, the direction of the field is your thumb, right? Now they've got a different way of doing the right hand rule in that picture of the hand. All right, so they're just doing one loop, but it gives you the same result. If your thumb is in the direction of the current, your right fingers curl in the direction of the magnetic field. So at the middle of the loop, it's going from right to left. And that is reflected in this cutaway diagram B. All right, so in the cutaway, they've got a bunch of field lines, and in the top row of the cutaway where my cursor is right now, you see a bunch of X's. All right, that means the current's going into the plane of the paper in that top row. And down here, where my cursor is now, in the bottom row, you see some dots. All right, and they seem to be misaligned, but they're dots. That means the current's coming out. So if you put your hand up there, it'd be kind of like clawing around from bottom to the top. That means that inside the magnetic field is from right to left, and that's reflected in those blue field lines that go through the middle. Now you got other field lines, and what you want to remember is that the field of a solenoid is kind of like the field of a bar magnet. It's almost it's not exactly a dipole field, but it's fairly close. And you can make it as close as you want to a dipole field, but it's kind of like an extended dipole field with a little stretch. In the middle, in the very center of the solenoid, is where that field is the most intense. Now, what your starter does in your car, it puts another coil inside there. And that generates current to actually crank the engine over. Because the engine is this big block of steel parts, right? It's really heavy. So you need a lot of work done to crank that baby over. So that's what they do with the starter solenoid. And there's all kinds of other solenoids in, and if you guys ever get into med school and survive med school and become a doctor, an MD, or a radiologist of some kind, you'll have to know a little bit about solenoids because they don't have them on defibrillators, but they have them on a lot of medical devices. And in fact, I think CAT scan is a big solenoid. You go into that tunnel. It's a big I think that's a big solenoid. So I've never studied CAT's CT scanners, but I think that's what it is. All right, here's the magnetic field formula. It's pretty cinchy. We're going to calculate one in a minute. Now there's mu naught, the permeability of free space. All right, and that purpley arrow represents the direction. Now, little n, lowercase n, that's the number of loops in your solenoid per meter. Right now, we're going to do a calculation with that in just a second. And then, of course, I is the current through the coil. Now, the reason that factor of n is in there is basically you got a stack of coils per meter. All right, so every meter you got so many, a stack of so many coils, and each of the coils in a solenoid is going to be identical. So you're going to get a lot of addition. So it's basically a multiplier. If you just had one coil, n would be equal to 1, and you'd be done with it. But so if you have a long solenoid, you got more magnetic fields, more loops, more coils, and you get a lot more Teslas in there. All right, so now what we're going to do is do a calculation. All right, so let's go back to the document cam, and we'll just do a simple calculation of solenoid field. It's not too bodacious. All right, solenoid field, and the magnetic field magnitude is mu naught times N times the current I. All right, so N is equal to loops per meter of the solenoid. So N is like a design feature. You set that. When you make that coil, you choose the right size wire, you can get 10 loops per meter. You take another size wire, you could get 1,000 loops per meter. So that's something that you can, and also it depends on how tightly you wrap it. Also, if you make another layer, sometimes they make these electromagnetics, they get a bunch of layers of loops. So this is just a simplified, idealized one. Let's use I equals 2.5 amps again, good old 2.5 amps. And of course, mu naught, we already know what that is, 4 pi times 10 to the minus 7 Tesla meters per amp. All right, here we go. And let me draw. Here's my coil. And let's do like the textbook, and let's say that these are X's up here, and down here we got dots. Okay, so that means that the magnetic field in blue, use my blue ink pen here, is through the middle like this. Now, outside the solenoid, use a different formula and a lot of trig and a lot of calculus. But right through the middle, right down the pipe, you use this formula right here, right? So there's my magnetic field direction, and up here is my magnitude. All right, so let's calculate that. Oh, one more thing I want to show you. This is a little bit like a bar magnet. It's not exactly the same, but so you got, kind of a dipole field, symmetry like that. Okay. Boy, this thing keeps fading in and out, even when I speak. Did you see that? Look at that. Hey! No, that didn't cause it to fade out. Anyways, I'm sorry, this thing is very, very bodacious here. All right, so let's calculate. B is equal to 4 pi times 10 to the minus 7 Tesla meters per amp times, all right, and let's use 100. Let's use 100 loops per meter. Okay, so 100 per meter, and then 2.5 amps. Okay, so this is something you could build in the lab. All right. Now let me use my red ink pen to cancel meters. Okay, so the constant mu naught has a meter in the numerator, and loops per meter is in the denominator. And then I cancel amps. All right, so they're out. So now I just have Teslas. All right, so now we just calculate. So this is 4 pi times 10 to the minus 7 Teslas times 250 over here. And let's see, that's 12 times. So this is about 0.003 something. Anybody verify me on that? All right, there's the Tesla level. All right. And side note, this is much, much greater than the magnetic field of Earth parallel component. So that's just a side note on our previous calculation. So this is a solenoid field, and so if you're ever doing a CAT scan, you got to know that that thing is well insulated. It's built like a tank. And part of that is to do good insulation so that when you get wheeled into the CAT scan tunnel, you don't get fried by anything. You know, if can you imagine some little kid going in there? Oh, and by the way, you've got about 1,000 amps going through this, and the parents are over to the side, they're going crazy. But you can't have it. So it's got to be well insulated, and so it's built like a tank. All right, go back to the document to the laptop. All right, so much for that calculation. Very simple, very basic. Now, go ahead to the next slide. Uh, this is a diagram. This is our objective for today. So let's spend the last few minutes on this. The force between two wires. So you have current 1, current 2 in this diagram. And each generates magnetic field lines around itself. Right now, this diagram, A, has magnetic field lines around current 1. Right? The field is going straight up the page. So the field lines kind of curl around in front and then around in the back. All right? Now, current number 2, a distance r away, has got moving charge. All right? So it's going to feel a force related to that magnetic field. And if you look at diagram B, you'll see the direction. It gets attracted to the other. So there's going to be a mutual interaction. All right? Now this is a force. And remember, in the Coulomb interaction, it was Q1, Q2. Now what we're going to find here is that it's going to be I1, I2 in the numerator. All right, so let's take a look at that. Please go to the document. Next slide, please. All right, now let's do this very carefully. All right, and so here's wire 1. And there's current going through it. And let's say that this length of it is L. All right. So the amount of so QV is equal to IL. All right. And why do we need QV? Because the magnetic force is QV. If everything's perpendicular, it's just QVB. All right. So that's why we want to know about QV. All right. So think about it. This one's the units of IL are Coulomb per second times meters. All right. And that's the same as Coulomb times meters per second for speed. So this quantity here, IL, is going to give us the force. Now the force on wire 1 can never mind, stay there. The force on wire 1 is equal to the current QV of wire 1, so that's QV, times B2, the field produced by wire number 2. All right, so that's this. All right, now B2 is equal to, all right, so here's wire 1, and then B2 is equal to mu naught times I2 over 2 pi r. All right, so that's B2 right here. Okay, and so now you can see that this thing is shaping up. Now I'm going to divide both sides by L. So this F1 over L is force per unit length on wire 1, and it's equal to, okay, mu naught times I1, I2 over 2 pi r. All right, and that is the force between two parallel currents. Now if they're not parallel, you got to do a bunch of trig. It's kind of nasty. But for parallel currents, now these are parallel. If they're opposite directions, they'll repel each other. So this is for parallel. They attract. Anti-parallel currents, they repel. And so you can see that the SIGN of the current is similar to the SIGN, or it has the similar effect as the electric charge in the Coulomb interaction. If you change the sign of the charge in one of the terms in the Coulomb interaction, it changes from attraction to repulsion, or from repulsion to attraction. Same thing here. In addition, you have two sources. So make a note of that. Your numerator has each source. It is a mutual interaction. The difference is the denominator is r, not r squared. So that's a little different. But we're doing all right. Now, go back to the laptop, please. Now, your homework for Friday is read up to 23.2, and I'm going to try to do some annotations tonight. All right, you're dismissed. Good class today. I'm very happy you did good on the brain burner. All right, put that in here. We'll take some photos in a minute if we have a second. All right, let me come up here. Ah. Oh. All my grunting and all my grunting and groaning is in YouTube now, immortalized. All right, let me